Hello everyone, my name is Rijal Mukherjee and I'm a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. So I will be conducting this session for NPTEL course on computer organization and architecture. We will be solving some sample questions in the form of tutorials, and the questions will be similar to the ones which we will be solving for this week's assignment. So this session is being recorded and it will be available for all the students. So let's start. So this is the first question. What will be the binary representation of 3.6c, uh, which is base 16? So this is a hexadecimal number. So the procedure for solving this kind of question is, so we need to find what is the binary representation of this hexadecimal number. So the very simple solution is you divide each of these hex digits and write the corresponding binary numbers. So it will be something of the sort of like this. So what is the binary of? So one thing is that you need to remember all the binaries and the corresponding hexadecimal. I guess it will be very helpful for if 0 0 0 0, it will be 0, 0 0 0 1, it will be 1, 0 0 1 0 will be 2, 0 0 1 1 will be 3, 0 1 0 0 will be 4, 0 1 0 1 will be 5, 0 1 1 0 will be 6, 0 1 1 1 will be 7. So sorry. So this is the hexadecimal number, and this is the binary number and the corresponding hexadecimal numbers. So similarly, if we continue, the last number will be 1 1 1 1 will be f. So this table you should remember, everyone. Like, this one is very important. So the binary representation of this will be 0 0 1 1. Then there will be a decimal point. 6 will be 1 0 1 1 0, and E will be 1 1 1 0. So this is the corresponding binary representation. Of 3.6e. Next we will go for the next question. So the question is, what is the 2's complement representation of in 16 bit? In 16 bit, what will be the 2's complement representation of 43 and minus 43? So these are 43 to the base 10 is basically a decimal, and minus 43. So what happens in 2's complement? So if you remember your lectures, so in 2's complement representation, positive number are represented as it is, and negative number is basically represented as 1's complement, and then 1 is added. So let me write. So for positive number 2's complement equivalent to the binary representation. For negative number, 2's complement is equivalent to 1's complement plus 1. So for the positive number, so we'll write 43 10. So the corresponding binary will be 0 0 0 0 0 0 0 0 0 0 1 0 1 0 1 1. So let me show it also that how it is coming. So 43 can be written as, so 43's binary will be 22, remainder will be 1, 2 11, remainder will be 0, remainder of this will be 5, remainder will be 1, sorry, will be 21, remainder will be 1, 2 divided by 21, answer will be 10, remainder will be 1, 2 divided by 10 will be 5, remainder will be 0, answer will be 5, 2 divided by 5 will be 2, remainder will be 1, divided by 2 will be 1, and remainder will be 0. So this is the corresponding binary. So for 16 digit it will be 1 0 0 0 0 0 0 0 0 0 0 0 1 0 1 0 1 1. Okay, now for the negative number we will find the, for minus 43 10. So what we will have to do is take 1's complement of this plus we'll add 1. So how to find the 1's complement? So finding the 1's complement is very simple. So you just reverse the bits of each bit of this string. So it will be basically, now we can write that as 1 1 1 1 1 1 1 1 1 1 0 1 0 1 0 0, plus we need to add 1. So the answer will be 1 1 1 1 1 1 1 1 1 0 1 0 1 0 1. So this is the positive one and this is the negative. So this is how the 2's complement representation of 43 and minus 43. So now let's go to the next question. So the next question is, if 73 to the base x, that is in x number base system, is equal to 54y in the base y number system, then the value of x and y are which of the following? So the question is little tricky, but let's understand what do you mean by base. So when I say base 2, what does that mean? That all the digits in this number system can have only two values, 0 and 1, so which we call binary. Now when we represent base 10, that means all the digits in this number system can have the values, can have 9 values, that is 0 1 2 3 4 5 6 7 8 9. This is called decimal. And also there are base 16, that is called hexadecimal. So again then we have 16 such numbers that can be represented. So 0 1 2 3 4 5 6 7 8 9 11 12 13. Oh, sorry. A, B, C, D, E and F. So these are the hexadecimal numbers. So these are called the base number system. These are different: base 2, base 10 and base 16. So if you count, each of them has 2, 10 digits and 16 digits respectively. So here it is said 73 is the number in X base system, and 54 is the corresponding number in Y base system. You need to find out what is the value of X and Y. So suppose so let's there be arbitrary another base system. So like if we say base 3, base 3 could correspond, means it can have only C3 value, so ternary something. So here it is called base X. So base X, so it is basically written 73x. So suppose I have a number of base 10. Suppose I have a number 123. How do I write it? 123, 1 into 10 to the power of 2 plus 2 into 10 to the power of 1 plus 3 into 10 to the power 0, right? This is the 2's place digit, this is 1's place digit, and this is 0th place digit. So that is how it is written. So that is how the decimal comes. So similarly, if we have a number size 101, so how it can be represented? It is 1 into 2 to the, so this is suppose base 10, base 2, and suppose base 10. So this can be represented as 2 to the power of 2 plus 0 into 2 to the power of 1 plus 1 into 2 to the power of 0. So it's basically 4 plus 1 0, sorry, 4 plus 0 plus 1 5. So this is how the base system works, like how what is base and all. So it is given, so there is a number 73x, and the same for same number in base y is 54y. So these are basically same numbers in two different base. So the question is, what are the possible values of x and y? So its decimal will be, what will be this decimal? The decimal of this 73x, it can be written as 7 into, like corresponding to this, like just like how we have done it, 7 into x to the power of 1 plus 3 into x to the power of 0. Its one, how it can be written, its decimal, 5 into y to the power of 1 plus 4 into y to the power 0. So these are basically same numbers, so we can write as equal. So therefore the equation becomes 7x plus 3 is equals to 5y plus 4, or 7x minus 5y is equals to 1. So this is the equation that becomes. So to find the solution of this question, you need to choose from these values a, b, c and d, by substituting which value this equation gets satisfied. So if you notice, uh, it is 7x minus 5y is equal to 1. So what it will be? So if we substitute all of these values, that is a, b, c and d, you need to find out which satisfies this equation. So if you substitute the option d, it becomes 7 into 8 plus 7 into 8 minus 5 into 11, so that is 56 minus 55 equals to 1. So uh, this this equation is satisfied by the value d, that is 8 comma 11, by substituting this. Okay, so that is how it will be done. So option D is the correct answer. So let's go to the next question. The next question is, consider a hypothetical processor with an with a instruction of instruction type LW R1, comma 35 R2, which during execution reads 32-bit word from the memory and stores it in a 32-bit register R1. The effective address of the memory location is obtained by the addition of a constant 35 and the contents of the register R2. Which of the following best reflects the addressing mode implemented by this instruction for operand in the memory? The options are immediate addressing, registered indirect addressing, index addressing. So basically, if I explain it in more simpler terms, the question asks, so if for this instruction LW R1, comma 35 R2, what kind of addressing mode is this? What kind of there is a processor that support this instruction. So the question is, what is the addressing mode? So let's look at all the options and then come to our conclusion that which is the correct addressing mode. So let's start. So number 1 is immediate addressing. So what do we know about immediate addressing? So so it has been taught in this week's lectures, like what is these addressing modes and all. So in immediate addressing, so a simple example of immediate addressing is, suppose this instruction, move A, comma 35H. So what does this instruction does? So this instruction basically transfers the value the 35 to the register A. So this is the operation basically it does. So so if we look at the instruction, how it will look like. So it will have the opcode, it will have the register, and it will have this value, this 35 value. So here you see um, the mm, the value that has to be stored in the register is basically present in the instruction. So this kind of addressing is called immediate addressing, where the processor doesn't have to fetch the memory from has to fetch the data from the memory. So this kind of addressing is called immediate addressing. Next, for register addressing. So simple register addressing can be shown as move A comma B. So what does this perform? This transfers the content of register B into content of register A. So the corresponding instruction register instruction register will look like this. So there will be the opcode, there will be reg1, there will be the source destination register, and there will be the source register. So this is the source register and this is the destination register. So the value of B is transferred to value of A. So again you see here the instruction has a opcode, a register, and a register. So this kind of addressing is called register addressing. This kind of addressing is called register addressing because obviously both the operands are registered. So let's look at the third kind of addressing that has been mentioned here. Register indirect addressing. So one example of register indirect addressing is, suppose this, move A this means so if this is the memory location, so here and suppose this starts at 100, 102, 104, 106. Suppose the here the instruction basically specifies, so if B contains suppose the value 104, then in A the value of this location 104 will get transferred. So basically A contains an address in the main memory. So B basically here contains an address in the main memory, and that and the data from that address location is stored in A. So this is called registered indirect addressing, because here if you look, though it will be range, though both the operands here are registers, but the operator specifies that the value that is stored here in range 2 is basically a memory address location, and the objective is to transfer data from that memory location to the register A. Now let's look at the last one. Index addressing. So one index addressing example I will write here is, suppose move A 10b. So what happens here? Suppose this is the memory, this is a register B. So value and A is stored by adding 10 to this, to the value in register B. So B here is a called a special type of register that is called index register. So this index register is basically so this index register uh, mm, index register contains a specific memory address location. So this instruction says that okay, let's add 10 to the address that is stored in B and load the data from that location. So this example is typically considered a looping statement where you need to move mm, through a chunk of memory. So in those kind of cases, this thing can be a situation that can be thought of. So 10 is added to the base address of B, and that address location is being fetched from the memory. So this address this is called index addressing the method. So now if you look at this statement LW R1 comma 35 R2 1 minute. So it says LW R1 35 R2 R1 35. So what it does is so if this is the main memory, and suppose this is the register B. So suppose it has, so this is the location 100, 102, 104, 106, 108, 110, 112, 20. So suppose if the base address is 100, so this instruction says load the data from the suppose this is the 135th location. So the instruction says loads the data from the 35th. Sorry. So this is suppose it is this location. That is 35th from this address location. So suppose this is 135. So 100 plus 35 is added, and the corresponding memory location from here, this data this is the location, and that is being loaded to the register R1. So so as discussed here, so what kind of addressing this instruction represents? So it represents the index addressing, right? So it represents a index addressing. index addressing. So basically, this question sort of a recap of what was taught in this week. So it's a quite nice recap for that purpose. So now let's go to the next question. So next question is it is similar to the previous one. Uh, so the question is from the previous question for the load instruction R1, 35 R2, what will be the effective address of the memory operand if R2 is 200 in decimal? So we'll say that LW here is R1, 35 R2. So given memory operand effective address of memory operand, that will be basically value so not it is not value, it is basically address val stored in R2 plus the index 35. So what is the value stored here? 200 plus 35 to 35. So it comes from the same concept that so suppose this is R2, this is 200. Suppose this is the base, it is stored. Suppose this is the 35th location. So this is the 0th location and this is the 35th location. So we add 35 to it and fetch the data that is stored here. So that data is being loaded in the LW is a load operation, is loaded in the R1. So that is the content of R1. So the data that is stored here is basically the new content that is stored in R1. Okay, so let's go to the next question. This is a continuation of the previous question it was. So the next question is, so a processor has 40 distinct instructions and 24 general purpose registers. A 34-bit instruction has an opcode, 2 register operands and an immediate operand. The number of bits available for immediate operand field is, okay, so there are many information that is given here. We need to grasp one by one each of them. Number one, there are 40 distinct instruction for the processor. Number two, there are CPU has 24 general purpose register. So, and it is being said that the instruction is 32-bit. Now it is being said that this instruction has 4 fields. So one is opcode to register 1, to first register, second register, and there is a immediate part. So we have shown previously the immediate part. So if you want a visualization, you can consider it as the previous example only. Load R1 35 R2. So as you can see, there is a, so LW uh, operation will have a specific code, that value is an opcode. So the address of register 1, so each register also will have an, so basically each register is distinct register, so you need to give a name to it, so that is an address. So every register has an unique address field. So that is this one. R2 also will have a specific value, and there is this basically an immediate field. So you can, if you want to visualize what kind of instruction is this, so you can consider this. So this LW R1 35 R2. So it is being said there are 40 distinct instruction and 24 general purpose registers. So you need to and it is also being said that this total instruction is 32 bit. So it is said that we need to find out the number of bits that is available for the operand field, immediate operand field. So we need to find what are the um, number of bits that is left, that has been that is been like that has been left for this immediate field to represent it. So so first we need to find what is the size of this opcode field. So how that is can be find? So the question says there are 40 instructions. So we need to identify each instructions uniquely. So how many bits required it will be? We will require 6 bits. You will the question will be how it is 6 bits. That is because the nearest number of the nearest power of 2, that is nearest to 40, is 64. So 64 is greater than 40, greater than 32. So you need basically 6 bits to represent each of these 40. So you may ask how they look like. So basically these are address fields: 0 0 0 0 0 1 0 1 0 1 0 0. So this is 40. So you see, for representing each of them you need 6 bits. So this will be 6 bit. Next it is said there are 24 uh, 24 registers. So for representing 24 registers, again you will require 5 bits. Now the same concept, basically 32 is greater than 24 is greater than 16. So basically 5 bits will be required. So it will start from 0 0 0 0 0 0 0 0 0 1, and the last one will be 0 1 1 0 0. So this is the last address. So this field will occupy need 5 bit. Again, register 1 will require 5 bits. So the question says there are 2 register operand, so this will also require 5 bit. So now if you see, so how much is left? 32. So this field will require 32 minus 6 minus 5 minus 5, so that is 16 bit. So this place will require 16 bit. So the immediate field is basically immediate operand. One minute. So basically immediate operand will need 32 minus 6 minus 5 minus 5 is equal to 16 bit. Clear? So this will be 16 bit. So I will again repeat what we have done in this problem. So basically the question is 32 bit instruction, so it is a 32 bit instruction. Each one, so the register, the instruction has an opcode to register operand. So this is an opcode, this is a register operand, and another register operand, and an immediate address. So we've shown up example of this address. This can be load R1 comma 35 R2. So this is an example of the instruction which you can find a little bit similar to. So because it has a opcode, it has 1 register, 2 register, and as an immediate part. So we then said so to represent 40 instructions, to represent 40 instructions, you require 6 bit, because 6 is the number of bits that is that is equal to we shown that that is the number of bits that is required to represent each instructions uniquely. Then for each register we need 5 bit, because obviously 24's nearest 2's power is 32, 2 to the power 5. Again we show each of the addresses how can it be represented. So the immediate part will be 32 minus 6 minus 5 minus 5 equals to 16 bit. Okay, now let's go to the next problem. So the answer is 16 bit. So now let's go to the next problem. This says the MIP instruction, consider the following MIPS instruction: SLT, T0, S0, S1. So what does the instruction do if S0 and S1 is loaded with some data. The options are A, set T0 equals to 1, um, if S0 is less than S1, B, uh, $T0 equals to 0 if $S0 is greater than S1, set T0 equals to 1 if $S0 is greater than S1, C, T0 equals to 1 if S0 is less than S1. Okay, so MIPS instruction was part of this week's lectures, week 2 lectures. So, what is SLT instruction? So, SLT instruction, what does it does? So, it sets the register content to the value 1 if the first source register content is less than second first source register content is less than second, else to value 0 if for vice versa. So T0, so this is the theory, so this is the property of the instruction. So basically T0 will be set to 1 if S0 is less than S1. Also T0 will be set to 0 if S0 is greater than S1. So the correct option will be T0, sorry, will be option A and option B. So this was a very straightforward theoretical question that so if you can go through the instructions that were taught in the week's lecture, it will give you a clear idea like what are the different kinds of MIPS instruction, what are their properties. So these kind of questions may come for your exam and for the assignments this week. So okay, that was the final question. So if you have any doubt, you can write in the forum, and we will meet in the next week's course, same time at Saturday, not Saturday, same time at Tuesday 6 p.m. Thank you.